stellar evolution. Now, I've talked about this before with you guys, about my feelings on outer space and whether things exist. But the thing that I want you to think about is this: is that stars are a lot like people. Now, I'm not talking about the fact that they have jobs and they go to work and things. I'm not saying that. I'm saying they're a lot like people. Their life cycle is a lot like people. And so what I try to do is I try to put it to where you guys understand it in people terms, and I think it'll make a lot of sense. So the question is, how do we know what their life cycle is? Well, um, first of all, things start out in a very simple way. We call this stage one. Stage one is a nebula. It's gas, right? And so clouds of gas and dust are out floating around out in outer space. And so what they're doing is they're just sitting there. Now, what I want to show you is a picture of what I'm referring to here. A second. And I'm going forward in time here. So when I think about a nebula, I think about like the Trifid Nebula. Here's a good example. A lot of gas and dust that's out here. And basically, this is the beginning of where stars are. And you might have a star right here where this bright spot is about ready to kick over. These are stars here in the background, but that's the Trifid Nebula. And we'll talk about nebulas here in a minute. But the reason why I tell you this is that if we think about the gas that's there, 70% is hydrogen, 28% is helium, and then only a very, very small amount is the heavier elements. Now, think about this, right? Hydrogen and helium. What's a star made of? Hydrogen, helium. That's right. Majority. If we look at our sun, the sun, right? Our closest star. The reason why we have energy is because we're converting hydrogen into helium through the process of fusion. We're fusing two helium atoms together. So if you look at the periodic table, hydrogen has one electron. If you bring two hydrogen atoms together, you now have two electrons. What's the number of electrons in helium? Two, right? So it makes sense that we're fusing these. Now, where do the heavier elements come from? Well, that's pretty simple. As the star gets older, we see more and more heavy elements. We'll talk about that in a minute here. But because it's so gassy, right, there's not a lot of gravitational attraction going on here. So because it's gassy, it's wafting around out in the atmosphere. We have very, very, very big distances, right? We might have some gravity, but maybe a molecule is as much as, I don't know, I'm making this up, 100,000 miles apart. And I don't want to use a standard system, but basically, we have real weak gravitational attraction because not a lot out there. And so when we think of stage one, the first thing we have is a protostar. So proto basically means baby in this case. So we've got a bunch of gas, and the gas is sitting out there wafting around in outer space. And as it does, it starts to collapse on itself. And when it does, it starts shrinking and spinning. Now, we're talking a big area. Trillions and trillions of miles of gas coming together on top of itself. So as we bring together, as it comes together, as it collapses, we increase the gravity, which means we have increased matter in an area, right? Because we're bringing more and more stuff in, gas, dust, debris, leftover broken planets. And then we're increasing our pressure. So we've increased gravity, we've increased matter, we've increased pressure, and then from there, because we've increased all that, when you increase pressure, you increase temperature. So in the process, like now you've caused the beginning of a star. It's funny. When you increase pressure in an air tank, the air tank gets hot. Why? Because when you increase pressure, you increase temperature. And so that's what's going on in outer space. This process is millions and millions of years in the happening. It takes a long time. And so eventually, though, we can get to a point of about, I don't know, 10 million degrees Celsius. And then we get the fusion. I talked about that earlier. Two hydrogens fusing into a helium, right? One electron now come to bind as two electrons. You look on the periodic table of elements, and you see that two electrons is helium. So this is nuclear fusion. Now, high temperature, high pressure are necessary for that to happen. Stage 2. Now, when I think of stage 1, I think of babies, right? Crawling, they've just been born, they're crawling on their hands and knees, goo goo gaga, the whole thing, right? What's going on? They're just been born, not mature, but eventually they learn and they grow up a little bit. And so as they start to grow up a little bit, they become a main sequence star. And just like people, this is the longest stage. We go from our baby stages to our adult years. And we're an adult, right? So we're grown up and we're very productive, long stage for us as well. We call this the main sequence stars. Main sequence. It's because they are the ones that are fusing hydrogen into helium. They're the ones who are really putting it out there. The energy is coming out, moving out from the center of the star out to us. That's what we're utilizing here today in Pontiac, right? So here's the deal. Why doesn't the star get bigger? Because gravity is pulling the outside of that star in. It's pulling it in, not letting it go. So while we have enough hydrogen available, it's stable. It's the point at which it's used so much hydrogen that it's no longer stable. In other words, it's fused it into helium and it doesn't have the gravity to pull back on itself. And so basically, it goes on to the next stage. Now, this is the longest stage in all stars, main sequence. Our sun, right smack dab in the middle of this thing, right in the middle. All right, stage 3, the giants. Okay, so main sequence star. I would say right now I'm a main sequence star in my life cycle, right? I've been hanging. I'm cranking out some serious energy. I'm making things happen. But some point, there's going to be a point in my life when all of a sudden I'm like, oh, I've had enough. I'm tired. I don't want to work as hard anymore. I need to retire. I need to relax. I need to do this. Well, the same thing happens with stars. That becomes the giant and supergiant stage, right? So, like when you get real to the point as a star where you cannot fuse any more hydrogen into helium. In other words, you don't have as much. What happens is the star, the gravity doesn't pull back on the outside of the star as much, and it starts to expand. I'll show you some pictures of this here in a minute. So we get a larger star. We call them the supergiants. And what's happening is they're nearing the end of their life cycle. So hydrogen's almost all gone. It's been fused into helium. All the energy's been released into outer space. Then the core inside the star is contracting because the gravity is trying its best to hold it together. But what happens is the temperatures go up. And what we saw on the scale is that when temperatures go up, the colors change to a bluish color, right? So again, we see fusion taking place, the helium and helium. Now, if we look at helium, then really what needs to happen is we have 3 heliums here. Helium has an atomic number of 2, right? Carbon has an atomic number of 6. How many heliums do you think you need to have to make a carbon? 3, that's right. So 2, 2, and 2 makes 6. And so what we see is now in the supergiants, we've made carbon. We've now made carbon because we're fusing helium atoms. Okay, so what happens is the star is cooling off because it's expanding. As the energy moves outward, it's expanding. And so because it's moving out, it's getting colder. And so as it's doing that, the colder temperatures mean that our color isn't as bright anymore. It's not the blues, the whites, the hot white yellows, or you know, blue whites or whatever. What we have is more of a red orangish color and more towards the red. And so it's getting colder. The last stage, just like us, right before we're prepared to depart this wonderful place, is the white dwarf. Now, I know some of you going, your hair looks like it's white dwarf. No. Um, when you get older, right before you're prepared to leave, this is when the star is about ready to lose all of its gas, all of the outer shell, and only thing left is it'll have its core. Now, where does that gas go? That gas is basically creating what's called a planetary nebula. So nebula is another fancy name for gas, right? And so what happens is the outer shell of the star gets released outside. It's let go. And then what happens? We have what's left, and that is the white dwarf. White dwarf is huge. I'm sorry, small, hot, dense core. Now, a black dwarf is nothing more than a white dwarf that's been cooled off completely. It's done altogether, right? Um, it's a dead star. Interestingly enough, I once heard that a teaspoon, people look for this stuff, a teaspoon of a white dwarf weighs more, I want to say it, and don't quote me on this, but I want to say it weighs more than a huge ocean-going ship. A teaspoon of it is like hundreds of thousands of pounds. It's crazy. Anyhow, it's because it's so dense. That's why. So basically, what happens is a black dwarf is nothing more than a cool off white dwarf. A nova, interestingly enough, a nova basically is a star that explodes, right? So it's a white dwarf, what was left of the star, that explodes, and then basically that material cools. Well, here's the thing, right? So we think about how long it takes for a star to explode, and then we think about events in people's lifetimes, and we now have video. They've recorded stars going supernova, right? And so what's cool about this is these stars, they end their lifetime and they explode with one great big bang, right? And so, interestingly enough, think about a time that you can think of in biblical terms where maybe you would have saw something like this, and then all of a sudden you start to think about, oh, you guys remember this song? Oh, little town of Bethlehem, how still we see thee lie. What was the light? The light was the star that was taking the three wise men to the manger, right? Right. And so what we now understand is supernovas do just that. They create this amazing light. Um, Again, supernova just blows my heart. Here's the deal: take all of a 500 million years of energy and put into one explosion. This will be an incredible fireworks show. What do we get out of it during that time? Hydrogen fuses to helium, helium fuses to carbon, carbon fuses to magnesium, and then we get iron. Our periodic table of elements is coming from the stars. People, you are the children of everything that is the stars, right? And you think about it. Neutron star, basically the collapsed core of a supernova. Again, it's very dense. Pulsars. I want to show you pulsars later, but basically it's a neutron star that's producing beams. All right, so again, a black hole. If we see white dwarfs And basically what happens is they collapse upon themselves. That is a star that's collapsed upon itself. The gravity is so great, it is a black hole. Nothing can escape from it with the exception of X-rays. So to look for a black hole, we look for X-rays. I'll stop here, and then we'll pick up here tomorrow.